Yeah, so thanks a lot for the invitation to speak here. I've learned a lot in this workshop. I think I started from an even lower point in my knowledge of experiments. I had a lot to learn, but it went fast, and I really appreciated it a lot. So I will tell you a little bit about nonlinear response through the lens of effective field theory. And my main goal is to convince you that effective field theory is useful, especially in strongly correlated systems where often you don't have other tools available, but also that it's predictive. So, you don't need microscopics to be predictive. Effective field theories can lead to sharp predictions that are, that can be tested and that are falsifiable and so on. And so I'll focus on two kind of canonical situations where we'll study nonlinear response, so metals and Fermi liquids more generally. And in the second part, we'll talk about the kind of really collision-dominated regimes, diffusive or thermalizing regimes. So, these are not the most exotic phases or situations you could imagine, but I think it's a good place to start. So let's start with metals. And to get started, I'd like you to think about a kind of funny system that has absolutely no nonlinear response. I think it's kind of interesting to start with this and then build on that. So if you consider a Luttinger liquid in one dimension, so perfectly linearly dispersing fermions, could even take it to be a free fermions. This system has exactly zero nonlinear response. And what's interesting is that it's not completely obvious that it has zero nonlinear response. So if you just think of, let's say, the density operator or the current, it doesn't really matter, but let's look at the density operator. So, it will have linear response, which you could see in the form of two-point functions. And naively, you might think there are nonlinear correlation functions, right? You could certainly draw diagrams that make these types of correlators look non-vanishing. But it turns out that if you there's many of them. If you look at a 14-point function, right, there's going to be many diagrams where you connect the legs in different ways. And it turns out that after the integrals, everything vanishes. Okay, and there's exactly no nonlinear response. Of course, there's a better way to see it, which is in terms of collective variables. So a Luttinger liquid, as you probably know, can also be expressed in terms of a boson. You can kind of think of this boson as a particle-hole excitation. And in this description, it's immediately obvious that there's no nonlinear response, okay? Because the density operator, the key difference is that the density operator is linear in the excitation. One second. So light will couple linearly to that excitation. If the theory is still Gaussian, which it is for linearly dispersing modes, you have exactly zero nonlinear response.
I guess there's an implicit assumption that your light couples to density or other variables in terms of which the Luttinger liquid is a free theory.
That's right. Yeah. So, well, yes and no. So the statement that so you have spin-on Fermi surfaces in mind, or is that?
I mean, yeah. So suppose my light would couple to psi, which should obviously can't.
That's my point. That's part of my point. The light does not couple to psi. Yeah. So that's why I'm saying, so these, I want to claim that these are the right variables. They're bosonic. First of all, light is bosonic. You should think of bosons. Okay. Yeah. But that's exactly my point. Yeah. So.
And you're ignoring photo emission.
Right. Well, yeah. But yes.
You said this to me the other day, and I didn't understand that. Maybe. So if it's a 1D, so you said this is true for non-interacting fermions. So I can choose collective variables, or I could just think about the 1D free electron gas. And in that case, it's certainly nonlinear if I have if it's linearized, the bands are linearized. So the only way I can get nonlinearity is if the bands are parabolic. So I don't understand.
No, it's not quite right. No. So yeah, for linearly dispersing, these diagrams exactly vanish. We can talk about it later. So in 1D, this is an exact statement. So linearly dispersing fermions have exactly no nonlinear response. Parabolic bands actually do have nonlinear response, and you can see it in terms of there are interactions in the bosonized description. Okay. Go ahead.
Like a comment, Peter, but that's how people study beyond Luttinger liquid physics.
Exactly.
They fermionize boson.
Exactly. Beyond Luttinger liquid physics is precisely. Yeah.
What if I did long-range interactions? So it was in the standard Luttinger liquid theory, would it still be true?
No, yeah, then that would get more interesting things could happen. Yeah, I'm gonna.
Presumably, this is a straw man example for you to set up the rest of your talk.
Exactly. But I appreciate the questions. I appreciate the questions. So indeed, as Andy anticipated, life is more complicated than 1D Luttinger liquids. But one thing that's interesting is that if you look at Fermi liquids, these nonlinear response is not zero, right? We're here for this, but there's still a remnant of this effect in the form of partial cancellations. So if you kind of just try to study nonlinear response, even in a free Fermi gas by computing these diagrams, you would have a kind of first guess of how they scale, and you would be wrong parametrically, and more wrong if you look at more and more nonlinear response. So there's an amount of cancellations that kind of increases with the amount of nonlinearities. And by the way, these cancellations do not occur in spin response, for example. So it's not that we're missing something basic. It's really coming from it's a little more subtle than that. And again, as I've kind of tried to convince you, a better variable to see this will be bosonic variables. So here, these bosonic variables are particle hole excitations near the Fermi surface. And the same way that there was no nonlinear response in a linearly dispersing Luttinger liquid because the bosonic description was free. In general, in higher dimensions, there are inevitable nonlinearities in the bosonic description, in the bosonized description of Fermi liquids. But they're very small. They're irrelevant in the renormalization group sense. And so they give you answers that are smaller than you might have expected from, let's say, setting out this integral. So they make these cancellations transparent and directly kind of give you the answer post cancellation.
So what calculation does it envisage? It's like because I'm bosonizing, but of course, particle hole continuum is a continuum.
Yes.
So what is grad phi in this?
You're
being deliberately.
So I was given 20 minutes.
Okay.
So I'm not going to. So I'm not going to give many details. So I will tell you. So this is
okay. So it's okay. That's.
Exactly. It's that's right. So there are many phis. Basically, there's a phi kind of living along the surface. Right. I can tell you more. Yeah. So there's indeed. So this is a kind of bosonization of Fermi liquids has been around for some time. But back then, these theories were Gaussian, were actually free, so they had no nonlinear response. And so what we did is understand the nonlinear structure. There's a kind of rigid nonlinear structure to this bosonized description that has to be there because you need non-Gaussianities. So some of these nonlinearities, and I'm really sketching them here, are really kind of universal and beautifully only depend on the geometry of the Fermi surface, whereas some others are a little bit less beautiful. So it turns out that there's kind of generalizations of Landau parameters for nonlinear response, okay, which tell you, for example, about still kind of forward scattering, but involving several particles. Okay, so that's kind of part of the data that will have to be in nonlinear response in a Fermi liquid. So there's a lot of this. There's a lot of parameters that might seem bad, but the point is that you're predicting. It's an overdetermined problem. You can predict whole functions worth of responses with a smaller set of parameters. So right. So what this effective field theory gives you are you can get these nonlinear responses just to kind of give you you can actually compute these quantities as functions of frequencies and wave vectors and so on. I'll just show you kind of the general scaling of these things. Linear response is what we all know. It's true to like, and you can look at for example, third harmonic generation and so on. Right. So there's several kind of things that we're thinking about in ongoing work in this context. One is whether what the scaling. So these simple scaling forms that one gets for Fermi liquids, how would they be different in quantum critical metals? Okay, is there room for subtle exponents? And so Peter asked, if we care about nonlinear response in metals, in particular two-dimensional or resolving several frequencies, I would say yes. I mean, I certainly care about it, especially not just to confirm these simple scalings, but to maybe characterize differences when you have beyond Fermi liquids type physics, non-Fermi liquids. Another interesting direction is to identify nonlinear observables where this complicated dependence on all these higher Landau parameters drops out. So there's a linear version of this, which is this perpendicular connectivity at zero frequency. where beautifully everything, all Landau parameters, effective masses drop out, and it basically just measures the shape of your Fermi surface. Here I simplified a little bit, but it measures the curvature of your Fermi surface orthogonal to the wave vector that you send it. This is a kind of nice thing because it just, it doesn't get renormalized. And it would be interesting to find nonlinear versions of this where we're thinking about that. I'll mention related work by Charlie Kane where they tried to, I think the motivation was the same. They were looking for nonlinear probes that in their case only depend on the topology of the Fermi surface. Unfortunately, it turns out that this one actually, so we did look into it, it does depend on this complicated cubic, Landau parameters, but I think there's still hope for finding some other probes.
Is that an equal time correlator?
This is an equal time, yeah. So they looked at equal time. And this, yeah, so this would be the Fermi gas answer, but unfortunately it's not robust. Good. So right. Okay. So for the second half, I'd like to slightly change gears and talk about a kind of different regime. This really collision-dominated thermalizing regime. So what I've said so far kind of works at intermediate frequencies. Okay, it's an effective Fermi liquid theory is an effective theory. It works at frequencies much smaller than the band gap, but also frequencies that aren't too small, because at very small frequencies, the system will thermalize. Okay, particle hole excitations won't really be the natural degrees of freedom anymore. Instead, there should be a kind of hydrodynamic description. So that's what I'll talk about now. And what's beautiful is that at these small frequencies, there's still, even though things are very complicated, it's collision dominated, there's still universality. In fact, it's even more universal because the system thermalizes. So just in pictures, interacting many body systems are complicated, but interactions also simplify things because they allow the system to thermalize. And so if you wait for long enough time, that the system will be described only by the only things that are left over, which are conserved densities. Right? The system will have quickly lost memory of its initial conditions. And the only survivors at late times are things that can't decay because they're conserved. So this could be charge, heat, spin, and so on. And of course, the dynamics, solving for the dynamics of these collective fields is much simpler than solving the full many-body problem. But the claim of thermalization is that it's basically all you need to do at late times because that's all what's left in the system. So this, as I said, this could be energy density in a spin chain, or spin density, and so on. And because the assumptions underlying this emergence of diffusion or hydrodynamics are so sparse, you're just assuming it thermalizes. This applies to a huge, a broad number of systems and setups. So this is what I mean by hydrodynamics. So, and you should think of hydrodynamics basically as an effective field theory as well. The degrees of freedom in the effective field theory are the densities. Those are the right variables. They're the right variables to work in because they're the ones that survive. They're the ones that are kind of perturbative in some sense. And typically in this regime, other microscopic approaches will break down. So in a certain sense, hydrodynamics has always been thought of as an effective field theory since its discovery, I guess. But the kind of first really action principles for hydrodynamic fluctuations probably came around the 70s. And since then, there's been a lot of developments, which basically culminated in a kind of systematic framework that allows one to really make quantitative predictions in hydrodynamics. And so one key point of these later works is that it's allowed to bring hydrodynamics and these theories of thermalizing system to a precision science, where we can, as you'll see, we can make predictions, check order one numbers, things work, and so on. So it's not just saying, things diffuse. We'll be able to say much more than that. So, okay, again, I don't want to give too many details. I'll just tell you what the degrees of freedom are in these effective field theories. So the players in the game are the densities that are conserved, and they each have a friend, an associated noise field. That's the kind of minimal set of degrees of freedom that are necessary to make sure fluctuation dissipation relations are satisfied. And then, the approach of effective field theory is to write down everything you can. So there will be many terms in general, but you do this in a gradient expansion so that, at long wavelengths, only a few terms matter. there will be higher derivative terms, further nonlinear terms, and so on. And the coefficients in an effective field theory are not fixed, right? So here I gave them names because they'll turn out to be the conductivity, the DC conductivity, or heat conductivity if you're talking about heat diffusion, and diffusion constant of the system. We won't be able to predict these numbers, but the power of effective field theory is in telling you that they enter in a bunch of different observables. One thing that we see here that's pretty interesting is that generically these effective field theories are nonlinear, and these nonlinearities here really come from actually linear transport. So if you have a system whose conductivity has some dependence on temperature or filling, or same for the diffusivity, this inevitably leads to nonlinearities. Okay, so what we usually think of as, say temperature dependence of resistivity, that's already a nonlinear statement. It tells you that there's going to be nonlinearities in your system. So there's really some rigid structure to these effective field theories whereby they tie linear response to nonlinear response. And so you can actually use them to compute nonlinear response. So this was done by my student Rutira Mishra at the University of Chicago. The same way you would work with any model you have, except this is an effective field theory that should apply to any diffusive system. Okay, that's the point of these effective field theories, is that they're very universal. And the claim is that you can get nonlinear response, arbitrary correlation functions of densities and currents in any diffusive system. So just to flash an answer, in gory detail. So this is what the 3-point function looks like, for example, and you really get the entire frequency and momentum dependence. Okay, and here the leading order only depends on things you could have extracted from linear response data, right? It depends on the conductivity and diffusion constant and how they depend on temperature or the quantity that's diffusing. Okay, their derivatives. So it's completely fixed.
But this is classical.
So this is for any thermalizing system, basically at low frequencies. Frequency is h bar omega much smaller than t.
Oh, yes.
So I'm assuming it thermalizes.
Okay.
At high frequencies, it won't thermalize.
Mm-hmm.
But it will apply to quantum systems as well. Yeah. So you can check these predictions. There's a lot of information here. So we just kind of looked at simpler situations where you have 2 times. This is more like Chi2 and not Chi3. And you can really test this in numerics and do really 0 parameter comparisons to numerics, because you could extract all the parameters that enter in this expression from linear response. Okay, so this is what I want to insist on. These effective field theories really have predictive power. You're not fitting a bunch of things. Everything is fixed, and these are 0 parameter comparisons. With these people, we did, so these people did slightly more serious numerics in flow case systems, where again, we extracted, we studied linear response first, extracted the diffusion constants, and then you can do this 0 parameter comparison of an entire scaling function for the 3-point function.
These parameters are not below.
So these parameters are not universal. Right? The diffusion constant is not a universal thing, but it enters in the same way in many observables.
So like there's some renormalization.
You get renormalized, but it enters, the renormalization enters in all. So it's very hard to predict the diffusion constant because it gets renormalized, but it enters in the same way in
Everywhere.
many. Yeah, everywhere. That's the point. Yeah, exactly. Very good. Okay, so in the remaining 2 minutes, I guess we did.
You have more than that.
I have more than that. Oh, I see. I want to circle back and go back to actually linear response and talk about how nonlinear effects can actually feed back into linear response in some interesting ways. So because often the correct collective variables are literally the densities, you should think of your theoretical description of these systems as being theories of densities. And if you see nonlinear response when you're shining your light on these systems, this tells you they have vertices. Okay? And these vertices can feed back into linear response. Okay? If indeed you have a description in terms of these densities. And what's interesting is that this leads, so in the case of diffusion, this leads to universal corrections to the 2-point function, to regular linear response. Okay? here I wrote it in space and time, but you can do this in frequency and so on. And this correction is actually completely fixed. Here I hit it a little bit. Let me see if okay, I didn't write it out. This function is completely fixed. So there's really no free parameter. It depends on d prime, like we saw before, but otherwise it's completely fixed. And you can test this in the numerics. So this is a system that diffuses. It has this kind of Gaussian behavior of the two-point function. It turns out that in this system, the diffusion constant is known exactly, so we could just subtract this leading behavior. And you see at late times here, I kind of collapsed the data so that it looks more or less collapsed, but there's a small deviation in the data. Blue is early times, yellow is later times. And if you look at this deviation, this slight, violation of scaling, and plot it here, this is what you get. So these are the various times. And the dashed line is the theory prediction, again, with no fitting parameter. Right? So this is really kind of just direct tests of these effective field theory ideas. One interesting consequence of this is that it tells you that thermalizing systems, so we all knew there were corrections to diffusion, but there's some that are inevitable and that come with coefficients that are completely fixed. This actually tells you that diffusion can't emerge too soon, right? Because it gives you a time scale. Here, this thing has units of square root of time. It gives you a time scale at which these loop effects become large, at which hydrodynamics becomes uncontrolled. So this is a kind of, IR bottom-up perspective on how fast the system can thermalize, right? It tells you, it actually gives you a bound that the local equilibration time of your system, the time scale at which hydrodynamics emerges, can't be too soon. Otherwise, hydrodynamics itself would be strongly coupled, and it's just not self-consistent for it to emerge too soon. What's interesting is that this is completely independent of the thermalization mechanism, right? It didn't matter if I had a spin chain, if I had quasi-particles, an insulator, or so on, because it just comes from these effective field theory ideas. So it's a completely universal bound. This is how this bound looks. If you add a few more assumptions that I can tell you about if you're interested afterwards, this actually leads to the Planckian bound, which there's been some interest in this bound in the context of high temperature superconductors. So I think there's a lot of information in these corrections, which you can also see in nonlinear response. And again, these are timescales that are probable in terahertz. So I think there's a lot of room to study these ideas experimentally as well.
Just how much of lifting is that a few more assumptions doing?
Yeah, so it's near a quantum critical. Because basically I just need some information of how diffusion depends on temperature, and let's get out.
So that's the time scale to thermalize?
It basically says it's impossible for a large class of systems to thermalize faster. Why? So this had been conjectured for a while, but people
Time
didn't know.
scale where the second term overwhelms the.
Exactly. It's not consistent for hydrodynamics to be weakly coupled, basically, because it has these huge loop corrections before that. So I'm going from instead of looking at the mechanism for thermalization, which will never be universal, I'm starting from very late times. We know things diffuse, and looking at what are the first corrections to diffusion when you start to see something else in diffusion. That's okay, so I think I'm roughly out of time, so I will stop here and take questions.
Is there a precise notion of when a theory becomes strongly coupled, like a Landau pole or something, or is it just a heuristic scale?
Yeah, so you can make it. There isn't indeed the cutoff of a theory is a bit. There isn't maybe a preferred definition, but you can make a sharp definition by just looking at a given observable and look at all the corrections and extract the time scale from there. So here I'm looking at this first correction. There are many others too. They might be more important. In fact, they are in some situations. So yeah, I think that would be one way to make this definition sharp.
I guess building on that, you did this for a particular example of hydro where one charge is diffusing.
Yeah.
So I guess the principle would be that there's actually several equilibration times somehow, because the correction, is it clear the correction is going to be, the scaling is going to be
so
the
let's
same?
say you have heat and charge.
Yeah.
If there are no thermoelectric effects, zero, then of course you could imagine there's two decoupled sectors.
But you're saying that
realize,
any cross effects will lock them, and then one
parametrically, I would expect it to be the same, and you could choose whichever is the longest.
There's not going to be a parametric. Eugene?
So actually, I have a couple of questions. So you had this statement that sigma perpendicular at Q as a universal form. I presume that's for the clean system, right?
Yes,
Is there anything universal for the disordered system?
that's a good question. That's a good question. Yeah, I'm not sure. Yeah, that's a very good question.
And another question. So, and this theory, actually, no, maybe another one. So when people did measurements with NV centers on metals,
yes,
you could see crossover from diffusive behavior, long length scales to ballistic transport. So can you guys do a better job in describing this crossover than simple Drude formula? Because what they use, they just sort of compare.
Yeah, so I didn't realize there was the need for something better. You're saying it's not very satisfactory. I'm
just curious if, let's say, one could do these measurements more carefully, whether one would see corrections to simple Drude scaling.
That's right. I think one could do that. Yes, I think one could be, could be more careful. So here you were saying as they were tuning Q, or as they were tuning.
Essentially, they were tuning Q, and I think the argument was that if you really go to short distance, strictly speaking, you would have to do Boltzmann equation, which nobody wants to solve, but maybe you have an alternative.
Yes. Yeah, this effective field theory kind of repackages Boltzmann equation.
Maybe a very naive one about Fermi liquid thing. So, but okay, I mean, I guess the new term that you put out in that characterize these linear response functions are irrelevant under RG.
Yes.
So do you have a sense of when an RG relevant term is relevant? Yeah, it matters.
That's a very good question. So indeed, these cubic Landau parameters, White and Landau have them. So they're indeed irrelevant for linear response. Okay? And that's the crucial thing. The point is that nonlinear response, in some sense, is zero. Right? That's what I meant by these cancellations. It's smaller than you would have expected if everything had a simple scaling. So nonlinear response only gets activated by what you would call irrelevant terms in Fermi liquid theory. And so you need to start, but there's a very precise way to know if you want a given observable how far you have to go in the expansion to get the first non-zero.
Okay, so but then does this mean that at long times this contribution decay?
No, because it's the only non-zero contribution.
Right. Yeah.
Yes.
Okay. Sure. But I mean, is it going to zero at long times?
That's kind of just the statement that here there's different powers of frequency than you might have expected if you just here it works. It looks like it works the opposite way. But if you write it in time domain, it would do what you say. Where if you kind of assign the scaling to density or current, you would get the wrong answer. You would get something much bigger than the right answer. And so it's kind of zero within that approximation. But that's the point. This is what you'll be measuring. Yeah.
What if, okay.
Perhaps a naive question, but is it possible to, with the effective equations that you come up, go to beyond perturbation theory to non-perturbative responses, as one would straightforwardly do, like with Navier-Stokes?
Right, non-perturbative in the sources. So in the external fields.
In the external fields.
Yeah. Yes, that's a very so there indeed you need. That's a very good question. I think it's difficult, but I don't think it's necessarily undoable. Indeed, like Navier-Stokes. So these effective theories are very similar to Navier-Stokes. Not necessarily the one I wrote for diffusion, but the one for Fermi liquids, where you could consider kind of macroscopic, as long as you are still, as long as these are still the right degrees of freedom to even think about this, which is not completely obvious. You could think of kind of macroscopic, going beyond fluctuations of these fields, right, as quantum fields, but just kind of coherent macroscopic semi-classical profiles. I think that would be something. But I think you're not guaranteed that you're still considering the right degrees of freedom in that regime.
So maybe one last question.
So say if you go beyond the Fermi liquid theory, what if the Landau interaction actually depends on frequency as well as angular coordinate?
Yeah.
Then is there any chance that those things have to show up? nonlinear response.
Yes, so that's basically, I mean, that's kind of what, right, that's kind of what so my way of doing this would be to couple this to a, you know,
Right.
say a critical or the gapless mode. And indeed, so I think nonlinear response will be very different. So I think there will be non-trivial critical exponents here
Right.
that are, right, that would be very interesting to see. You know, it seems like something that should be testable in say, strange metals, for example.